Okay, so we've got a group homomorphism alpha, which maps a group G to group H, and we have the property that for all x and y in group G, alpha of x, y equals alpha of x, alpha of y. I'm going to be a little bit more explicit. Remember, I'm being quite explicit, or trying to be explicit about this. I'm going to write the group G with a star, and I'm going to write the group H with a little circle like that for my operation. So this standard equation for the definition of a homomorphism becomes alpha of x star y equals, that should be an x there, alpha of x little circle alpha of y, because these guys, alpha of x and alpha of y, are members of H. So I'm going to ask the question, I'm going to find out some very basic properties of a homomorphism. What is alpha of the identity element? Well, it's the identity element of group G, because remember, alpha is a function of G, which sends it to H. So I really ought to ask what alpha of EG is equal to. I'm going to ask, what's that equal to? Well, what I'm going to do is to use the properties of the identity element in G. So I'm going to ask alpha of x EG equals alpha of x, simply because x times EG is equal to x, but it's also equal to alpha of x, alpha of EG. And I'm being a little bit slack again, because I should be writing my group operation there, because these guys x and EG are in G, and so we should really be writing the star. And this, of course, should be a little circle here, because these guys on the right hand side are members of H. So these two are equal. So that tells me that alpha of x equals alpha of x, alpha of EG. So I'm going to multiply on the left by alpha of x to the minus 1. Alpha of x equals alpha of x minus 1, alpha of x, alpha of EG. And of course, these guys here cancel out. So this one here, this and this is alpha, but alpha E. Because alpha of x is a member of group, oh no, put alpha E, it should be alpha H, I'm sorry, equals alpha EG, because these guys cancel out as well. And just to be absolutely explicit, this minus 1 operator here is inversion in group H, not in group G. So that tells me that alpha of EG equals alpha H. Haha, that's nice. That's what I wanted to show, and I've shown it, that the identity element maps to the identity element. If alpha is a homomorphism, then the identity goes to the identity, which is nice. And we've got that just from looking at the basic properties of a homomorphism, which is this equation here. Although, as I say repeatedly, you will see this version here in the textbooks, but what it really means is this version here. Okay, I'm going to stop there.